The topic of this section is line integral, also called curve integral or path integral or curvilinear integral. This is a generalization of the definite integral that we have seen in the previous semester. Let me start with a very simple physical application. If we push some object along a distance, when we apply some force, say 3 newtons, over some distance, over some displacement, say 2 meters, then we do mechanical work, in this case 6 joules. If we denote the force capital F, and if we denote the displacement S, then the work W is just a product of the force and the displacement. We will generalize this result in 3 ways. First, it may happen that the force is not constant. Then it may happen that the force acts in a different direction than the motion, than the displacement. And then the path may be not a straight segment, but some curve. And this will give the line integral. So, if the force is not in the direction of the displacement, say the force goes this way, then if we denote this angle phi, then only the component of the force in the direction of the displacement actually does the mechanical work. So instead of F, what is important is F times cosine of phi. So we can generalize this to Fs times cosine of phi. But if we denote the displacement as arrow as vector and F arrow as vector, then Fs cosine of phi is the dot product of the 2 vectors, S arrow and F arrow. So that was one generalization. If the force is a vector in the general direction, not necessarily in the direction of displacement. The second generalization, if the force is not constant. Constant force is a situation if you push something and you act against the friction. The friction may be constant. But if you say, if you deform a spring, then the force grows. In general, it may be a function of the position S, and then instead of the total work, we will consider the element of work over a small piece of the path of the displacement, and that will be the force times the small element of S. And now let's denote it R, because S is a good symbol for the length. But if we talk about position, then R is, as a radius vector, is more common, more frequent symbol for this. And then the total work will be integral from some position R1 to R2 F dot dr. Well, this is still when R denotes the position along a line. But in a more general setting, we can move something from this point to this point along a more complicated path, not just a straight segment. And then we can consider the total journey, the total path, to be divided into a large number of small pieces, and in each part we have a small displacement which is now a general vector in a 2-dimensional plane or even a 3-dimensional space, and this dot stands for the dot product. And then we will not denote the endpoints as R1 and R2, and we will integrate over a curve C. We have seen indefinite integral where no symbols are below and above the integral sign. We have seen definite integral when we have two numbers, two limits. So, nothing here, indefinite integral. Some number here, definite integral. And here, something below and nothing here. And C is not a number. C is a name of the curve, of the line, of the path. So, we should perhaps discuss a little in more detail what we mean by a curve, by a line. Let me start with a simple example. You know that x is cosine of t, y is sine of t, is a nice parameterization of a circle. If t goes from 0 to 2 pi, then in the xy plane we have one circle, one whole round. And then we can choose we can change the radius or the position and so on. So this is some function of t, some function of t. In general, x may be a different function, y may be another function, and specifying these two functions and the interval for the parameter t describes a curve. Well, we want the two functions to be nice. That means we want them to be continuous, and we want the derivatives to be continuous, and we want the derivative to be non-zero. Then this will be a smooth curve. In a three-dimensional case, we can add the third component, z, as a function of t. So we can have three functions. If these functions are constant, then we have one single point. If the functions are not constant, then the point moves in the two- or three-dimensional space. We can have even more coordinates. Well, and now we want to rewrite this integral into the definite integral. dr is the small element of the integration path. We can think of dr to be a vector with components dx, dy, dz. If x is a function of t, then the differential dx is the derivative of x as this function times dt. Similarly, the differential of y, dy, will be the derivative y prime dt, and possibly, if we are in a three-dimensional space, then z prime dt. Sometimes, instead of prime, the derivative with respect to time is denoted by x dot. So instead of x prime, sometimes we write x dot. And similarly, y dot and z dot. If we apply this to this curve, then we see that dx would be derivative of cosine, which is minus sine t dt, and differential of y dy is cosine of t dt. And if we denote the components of f, say f1 and f2, namely the component in the x direction and in the y direction, then this scalar product becomes f1 dx plus f2 dy over the curve C. Okay, let us consider some simple example for this line integral along this circle. Well, for this, let's consider just from 0 to pi. That means we consider only this half circle. Then this is the initial point of the curve, and this is the end point of the curve. And we move in this direction. Remember that there are infinitely many different parameterizations for each curve. And these split into two families. One of them describes the point going in specified direction, but some parameterization may describe the same curve, in the sense the same graphical object, but traveled in the opposite direction. Well, and to evaluate this integral, we want some function, some force. So imagine that the function f arrow in a point xy will have, say, two components. The first one will be 2, and the other will be, say, x minus y. Then this integral will be integral from t starts at 0 and t goes to pi. f1 is equal to 2 and dx is equal to minus sine t dt. We will write dt at the very end. Plus f2 is x minus y. X is cosine of t minus y, and y is sine of t. dy, and dy is cosine of t dt. Well, and this is the definite integral from the first semester, some number. Okay, we can compute this. Integral of sine from 0 to pi is equal to 2 multiplied by minus 2 is minus 4. Integral of cosine square when integrated from 0 to pi is equivalent to integrating 1/2. From 0 to pi is equal to pi half. And sine t cosine t is equal to 1/2 of sine of 2t. The antiderivative is minus cosine, and minus cosine evaluated at we should compute this more carefully. Minus integral from 0 to pi sine times cosine is 1/2 of sine 2t and sine of 2t looks like that, so the integral is 0. So the result is by half minus 4. In the next section, we will see more exercises to illustrate this line integral.